All right, good morning, everyone.
Morning.
Morning.
I just noticed logging in here. Good morning. I just noticed logging in here. It's June 1st. I wasn't really thinking it was June already. So thanks for naming the video so it's easy to find. And so good long weekend, everybody.
Yeah, how was yours?
Pretty good, pretty good. I hope we didn't lose too much. Wait for it. Okay. I hope we didn't lose too much momentum in our learning process, after a long weekend. Get it?
Good one.
My pet peeve, right? That's my pet peeve, the use of momentum in the wrong way. Oh, well. Any questions before we get going here? Just doing a little bit of attendance here. All right. Don't want to send her out, Dawson, but welcome aboard. It's good to have you here. Not sure if you got a microphone working there or not. All right, here we go. So no questions being asked right away. So we started into momentum on Friday and just saw the basics of it, like that momentum is mass times velocity. Maybe I'll just load up the previous lesson there quick. That'd be 48, right? Type 1 stuff like that. I'll just load the PDF, it loads quicker. So we saw just the basics that momentum's always conserved. And we started looking at just one-dimensional conservation momentum. So we didn't have to worry about that, on Friday's work, that didn't have to worry about the idea of like keeping the X's and the Y separate, like we'll have to start doing today. So I did mention here, the idea of this momentum M1V1, so momentum of object 1 plus the momentum of object 2 will, and 3 and 4 and so on, however many objects there are, right? All the momentums added up will be the same before and after. That's what this is saying, right? So each object's momentum added up before and after will be the same. And what else did we get to here? We saw, I basically proved that the conservation momentum is true using Newton's first and second law. So that's kind of nice to see that that's not just made up stuff. It's actually based on things that we know for sure are true. Went through a couple examples of one-dimensional conservation of momentum. We started talking about this idea of like, is it possible for a golf ball and so on, and that'll start to actually have more official meaning, more official predictions, I guess you could say, based on the next two topics we cover, like next two lessons of the topic we cover. So just to get us back on track, get our momentum going here. And so here we go. We already did that part there. So this is the next part. And so this is the one that's sort of harder to imagine that momentum is conserved. Picture like an explosion. It can be literally an explosion, like a grenade going off is an assignment question I have ready for you. Or it could just be like the little Pasco carts we have with the red and the blue carts, and we can have a spring in between them. And I think when you were playing with them before, I think a lot of people noticed it's just the spring. You can load it up and then release it, and it launches the cars each way and so on. So if before a collision, let's look at examples here and that. But if we have the two carts sitting there with no momentum at all, just both of them are stopped, and then you release the spring, and we end up with, each of them having momentum. The question is, if we don't have momentum, obvious, before and then after a collision, there's obviously lots of momentum. Is momentum conserved? Well, if we go back to this rubber stamp guarantee back here, way up at the first thing we did. All right, just to remind you, or where was that slide? There was a slide somewhere where I had, is there a previous lesson? What am I thinking of? And momentum's always conserved, and there was a rubber stamp saying it's always true. Maybe it was the lesson before that one. But yeah, I want you to think of it always as a, yes, of course it's conserved. Momentum's always conserved. So what you'd think of here is momentum going out in all those different directions, cancel each other out, right? So say you have momentum of like 1,000 to the up and diagonally to the right. Well, then there's going to be a momentum of 1,000 going down and diagonally to the left. They literally just all cancel out. And so when you're talking about the two-dimensional stuff, it gets a little trickier. Just want to make sure I'm on track here for what we need to be doing. So we did that. Yeah, this is where we left off, correct? We talked about the mass of the Earth and so on. Just feel like because the next, I'm just double checking to make sure I'm not off track and confused as to what I need to cover next. So I feel like I am, but maybe not. Keyboard here. I was flipped it around, but I'm gonna have to have it the other way. Just want to get my bearings here as to what we're doing next. Make sure I'm not skipping something. Bear with me. So yeah, because 51. Yeah, okay. So I just was thinking we were getting into that two-dimensional stuff today, but we're not even actually probably getting to that. All right. So it's hard not to start to think about the two-dimensional stuff in a collision like that, of course, right? So we're scaling it down to this simpler linear explosion type of situation. So let me just play that little video. That my YouTube video should still work here. So we're saying, we're calling this one, the blue one pushes on the red one. So I'm going to be releasing the blue cart's spring. So the blue one's going to push on the red one, I believe, on the second try there. So that one's, visualize that as the blue one pushed on the red one because the blue one's spring is the one that launched out, right? But of course, if the other video here is labeled as if we did another video where the red one pushes the blue one, there's really no difference because of Newton's third law, right? But at any rate, you could think of the initial momentums as 0 and 0 because they don't have any velocity at all in that video. I'll just hit replay here, right? So no momentum to start, and then finally on the second push, boom, we've got momentums that are visible, right? And so then we're thinking of one of them's in the positive direction, one's in the negative direction, whichever's which, whatever you decide to just define the positive direction, pretty easy to see that they're going to cancel out. You're going to have about the same velocities in the video, you can tell, and they have the same masses, so you've got a positive and negative that are going to cancel out. The second video is titled A Small Mass Pushes on a Large Mass. And so you're going to see a bunch of weights, a bunch of masses added to this red one. And so when you release the blue plunger here, what's going to happen? Take a second to think, what do you think is going to happen? Any predictions? One easy prediction would be about momentum, as a hint. Anybody brave enough to key their mic and make a prediction about momentum conservation with this interaction? Maybe it's too easy of a prediction. No fun. No fun. No one can predict that momentum would be conserved. Anyways, but this big heavy card's not going to go as fast as when it wasn't loaded up, right? And the blue one's going to go like crazy the other way because it's bouncing off a brick wall almost, right? So wait, just pause for a sec. Can you hear me at least?
Yeah, we can hear you.
All right. Your mics just aren't working, I guess, except for that one when I ask if you can hear me. Anyway, so launching here, boom, see the blue one going like crazy and the red one barely moving, all right? So momentum still conserved. Well, yeah, of course. What you're getting is, of course, 0 momentum at the start. And then you're getting these values here. I'm moving my circles by accident instead of those guys, but you're still gonna have a positive and a negative number, right? It's just think about how these numbers exist, right? You've got a small mass with a large velocity, and then you've got a large mass with a small velocity, and so you still have a small number and a large number multiplying together in both, so you could picture very easily how those would be the same values, same sizes, same magnitudes, if you will, right? So they're canceling out. So this idea of momentum's conserved, and it's good to start to see some situations where you might think later on, if you see it, like, wait a minute, momentum can't be conserved in that. Look at it, there's a bunch of momentum afterwards. Well, we're analyzing out that that's okay. It's okay to have momentum afterwards. Even if you didn't have any in the beginning, right? Because they're actually vectors and they're canceling out. So the next type you'll see in questions, this is again, just like the uniform acceleration questions, right? I could have done one lesson on solving uniform acceleration questions and then just said, go for it, right? But it would have been tough because there's all these different scenarios. You're given this, you're given that, and so on. Same thing here. This is all about conservation of momentum. We did the first case we talked about was whatever it was here, like the type 1, whatever I called it, right? Just the one-dimensional collisions where I tell you a velocity and velocities before and after, and there's basically one missing, and you solve for the missing piece. The next weirder case was like an explosion cases, just because they're conceptually, just visually a little bit different, right? Then the third one now, to be able to tackle different types of questions is if you're like picture walking in a canoe, or this canoe actually has little stabilizers on either side, so it's actually kind of like more possible to walk in a canoe, or just on a raft, things like that. The idea is, I'm sure you can picture this, if you've been in a light enough boat and you nose it up to a boat, or up to a dock, sorry, and then you try to like walk towards the dock. Have you ever had this happen where the boat kind of goes backwards and you kind of go forwards and you get to the dock and you're not necessarily meeting up with it anymore? Like it's just because of momentum conservation, right? So the idea is if you're here and your both velocities are 0, and then you decide you're going to start to walk forward, right? Then you end up with like a positive number here for you, and then matching, we can predict that it'd be a negative number for the boat, right? The raft or the canoe or the whatever you want to picture standing on. So, those same idea, you can picture those becoming 0, right? And you still have no momentum in the end. It's just that you're going forward and the boat's going backwards, canceling out. So let's do some numbers for this and see how it works. We've got a 50 kilogram person, an 80 kilogram canoe, no velocities at the start. And then your prime velocities, your final velocities are 2 for you relative to the Earth. Okay, and just make note of that, okay? It's like you have your phone GPS on and you walk so that your phone GPS says you're going 2 meters per second relative to the Earth, right? Rather than, the trick here is rather than relative to the boat, which is of course the easier one to actually think of, right? If you're thinking, oh, I'm stepping 2 meters every second measured on a boat, that would be your velocity relative to the boat. I want to give you for now your velocity relative to the Earth, because that's your separate system, right? Your separate reference frame that we know momentum is conserved relative to. So we're going to deal, I am going to actually deal with the idea of velocity relative to the boat as well, as part of this, just as a bonus, basically, to really understand everything. So to start with here, of course, we get the masses, M1 and V1 can go in, and M2 and V2 go in. And, as you write all this out, you're probably realizing, like, why am I bothering? Why don't I just write a 0? I'm writing it because I want to be really clear about what we're doing. But in your work, in your homework, you might just be like, well, I can put a line through. Let me grab my pen tool here. You could put a line through this and say 0, and a line through this and say 0, and just skip right to that if it's saves you a little bit of carpal tunnel syndrome at the end of the day. So we still have the masses, the 50 and the 80 are still the same. You've got the 2 in there, and then you've got the other velocity. So clearly we can just solve for that, right? So we end up with a 100 plus an 80 V2 prime, subtract 100 from both sides, divide both sides by 80. The math works out lickety split, and you have your velocity of the canoe. Okay, going the other direction, you can tell by the negative. Let's highlight that, right? It's in the opposite direction. Right, to what you decided to walk at. That's why that negative comes out of the math. Okay, so momentum conservation, still working for us. Good stuff, right? Any questions about that one? Do I need to leave that slide a little longer, or are we good?
I think we're good.
All right, thank you. So it's just another example worked out here. I'm not going to go through this one in detail, but this is the same deal, right? 75 kilogram and 55 kilogram, and the person starts walking. Notice again, it's relative to the water, right? So it's the exact same kind of question, just worked out again. If you want to try it from scratch, you'll have a solution here that you can look at. Okay, so I'm just going to go right through that, and you're gonna try it. Just good practice, right? So this is the page where I wanted to mention how I'm gonna talk a little bit about the idea of velocities relative to one another, right? So in grade 11, we did this where we looked at velocities in moving reference frames. So we said like the person, velocity of the person relative to the water, and the velocity of the person relative to the raft and stuff like that. So the one that I want to just maybe show first, actually, maybe is this one, velocity of the person relative to the raft. Actually, no, I'm going to go with this one. I do have it the order I want. So think of the velocity of the person relative to the water. If you're on a raft, you're walking, then the velocity of the raft and your velocity add up to be your total velocity relative to like the earth, let's say, rather than water, but same deal, right? If we're talking about water just sitting there on earth, you're not worried about current in the river for this. So basically you're walking inside of something that's actually moving, and so your two velocities add up. And certainly one might be a positive and a negative, but the whole point is they combine like good vectors do and give you your actual velocity relative to the bigger reference frame, right? So that means that we can solve for the velocity of the person relative to the raft if we wanted to work with, right? Velocity relative to the raft, because certainly that's going to be the easier thing to measure. If you're on a cruise ship, you're thinking I'm walking or I'm running down a hall in a cruise ship. You're not thinking necessarily about your velocity relative to the earth because you don't necessarily know the velocity of the cruise ship. That's the idea we're going for, right? So the velocity of the person relative to the raft would algebraically just solve to be this. We're just subtracting the velocity of the raft, of the raft relative to the water from both sides, right? So algebraically, we get that solution for what the velocity relative to the raft is. Now, I do have to maybe just use these numbers, unfortunately, here, because the numbers we did here aren't the ones I'm using in my example. I should rejig this next time around. But let's just cut to the chase here, and you see the answers you get, right? Basically, they're saying if you walk forward at 2.3, right? The calculations lead to the raft going backwards at 3.1. Okay, so to put this in terms of numbers here, your 2.1 plus the negative 2.3, say was 2.3? Yeah, 2.3 plus the negative 3.1 would give you your velocity relative to the water, right? So I think I have this here where this was 2.3 plus this negative 3.1. And you can see, okay, well, you're going to have 2.3. Is that right? 2.3 relative to the water, and the raft ended up going 3.1 relative to the water. The numbers just seem like they're too big. But the 2.3 take away the 3.1. I have the rest of the stuff going. So you have like negative 0.8 apparently. So the velocity of the person relative to the raft, the person was actually trying to walk at 5.4, right? So I want you to think about this, okay, and see if you can figure out how this would work. If you didn't have this analysis, okay, you wouldn't have known the 2.3 and 3.1. I'm asking a different question here where it's saying, okay, if you're on a raft and you know the masses of each of the, you and the raft, right? If you decided to walk, so your velocity was 5.4 meters per second relative to the raft, what would your velocities be relative to the earth, right? So that's obviously here, because we had the luxury of having this other example that you can look through and go through prior to that, right? These wouldn't have been known, right? But you should, if you have a full understanding of physics as a person, wanting to be able to predict everything in the world around you, you would think, if you are on a swim raft this summer and you decide you're going to walk at a certain rate, say 5.4 meters per second, the physics should be calculatable where you can figure out how fast you're going to actually be going relative to the water, and then correspondingly how fast the raft's going to be going. relative to the water, right? So that's what I want you to try to do. Okay, so that one is I want you to have some time to like think about this and try some things. Try some things, see if you think they make sense, right? After you've tried it for a reasonable amount of time, if you're not sure, you can take a peek at the solution set and give yourself some hints that way. Eventually, ideally, hopefully, you can sort of reason it out. I actually had this question in the notes from last time I taught this, and I don't know if I have the solution written down anywhere or not. So I actually had to do exactly what I'm wanting you to do. I had to sort of reason it out, like, okay, let's try some things. And I ended up figuring it out, but honestly, it wasn't my first try. Okay, the first try, I kind of got an illogical answer, and I was like, oh, that doesn't make sense. And so I did something else and ended up getting the numbers. Okay. I guess if I didn't manage to get the numbers worked out, I probably would have deleted the question, pretend it didn't exist. But I'm glad I was able to figure it out. So anyways, I hope you can just I'm challenging you to try to learn from this. Okay, and you do have those solutions there, so you don't have a endless, frustrating, never figure it out kind of experience. You can actually sort of reason it out in the end and make it make sense. So anyways, that is this challenge question is sort of something I want you to do as well. So it's there on that first page, it doesn't get forgotten. So these guys, if you want to take a quick screenshot of that, notice there's not a ton of questions here, just important stuff to practice, okay? So I'm hoping not having as much as some days gives you some time to feel like you can put some thought into this, not be rushed. Good deal? All right. As always, I take the eerie, awkward silences as emphatic nods. Yep, we're good to go.
Yes,
all right.
We're good.
All right, so yeah, let's look at the last type. I've divided this one topic into these different types here, as I've said. So we're going to look at the objects stick together type. You saw the video of the astronaut with the two tennis balls, and you have the Velcro attaching the balls together when they hit. So that's a object stick together kind of an example. The wording for this, which will make sense once we look at elastic collisions, is this is a completely inelastic collision. Okay, so normally if two balls come and collide together, you might visualize them compressing a little bit and then springing back apart, right? So that's the elastic word. So if they're compressing and then springing apart and giving velocity back, so you'd have some velocity stored as elastic potential energy, which we saw previously as Hooke's law, basically the compression distance times the force constant, however many newtons per meter you're compressing, right? So if you have some compression and then it all releases back out to energy to motion, kinetic energy, then you've got a completely elastic collision, whereas this one's the opposite of that. This one's the completely inelastic collision. None of the energy is coming back to kinetic. Okay, so they actually get stuck together, and that's the example I want to do next. So here we go. So we've got two objects sticking together, and another little video to show what I'm talking about here. Oh no, sometimes that happens. Let me just unplug my one memory stick and plug it in. Although, wait a minute, now I might not even be able to find that because I don't have a downloaded video to do that. So you know what? Just picture the carts. We know how the carts have Velcro. Some of the carts would have Velcro. They're just sticking together. So I guess I don't have a video to demonstrate that, unfortunately. All right, but looking at what we have, the idea you have to realize is that they become like a combined mass, right? So basically, because they're sticking together, you're going to have each of the velocities be the same as each other. The final velocity of each of them since they're locking together, they're going to be the same. So you could call each of them like velocity 1 and 2 combined, right? So basically, you could have a step where we could say, because they're sticking together, you get mass 1 and mass 2 lumped together. I have it so far as maybe they're both V2 prime, or they could have both been V1 and 2 prime. maybe I'll jot in a 1 and 2 there just because it's even easier to picture. So this is velocity 1 and 2, velocity 1 and 2 combined, scribbled in there a little bit anyways. Here we go. Something like that, whatever. You get the idea. So we can common factor out that common velocity. So that's going to be the 1 and 2 there. So we can common factor that out. So that's where you have that M1 and M2 combined, right? So you're going to, this is basically the formula, the version of the momentum conservation equation that you'd use. But I don't really think you're going to think of this equation right here as a new one to memorize. I'm not loading up the equation sheet and adding it to it. I really want you to think of it as more logic than a new equation to memorize, right? So you would be given numbers, of course, the idea is here, right? So typically you'd be given the masses and you'd be given the initial velocities possibly and asked for that combined velocity. Or maybe you're given the combined velocity and one of the initial velocities and you determine the other initial velocity, the usual, right? Give you a bunch of numbers, ask for the missing piece. Okay, so usually you're just asked for that combined velocity quite often, but certainly you could be given that and asked for what the initial velocities were. It's just that predictive power that we have because physics is so predictable. Okay, so that's the new thing here. So here's the example. We got two football players and one tackles the other and they end up in a heap on the ground, right? Clinging onto each other and attached together. So the way they give you the information as a paragraph, of course, you pull out your given information. So they say, oh, one person's 108 kilograms running at 9.1, and the other one is 91 running at 6.3. I would like to see you do an M1 V1 and an M2 V2. I mentioned on Friday that I personally find it a little easier if you sort of group them, than having them all in one area. It's a little bit easier to pull the right numbers when you need them. And they have the visual here of the different velocities and so on. Okay. So we are going to figure out the velocity they'd have as a combined group of football players here. I was going to say physics players for a second, but it's not the same. All right. So we know, obviously, like it says, momentum's conserved, right? And so I'm going to show my version first here. I just think it's a little easier to follow. I hope it's a little easier to follow. That's why I do it the way I do it. But M1 V1 plus M2 V2 plus M1 V1 prime plus M2 V2 prime, the final momentums. And so that's where I'm showing the final velocities are the same. They're together, right? So you have velocity 1 and 2 combined, velocity 1 and 2 combined, right? Common factor that out. And there's that equation that we know we can use. So at this point, just fire numbers in. You got your masses, you got your velocities, fire it all in, right? So the 108s and the 91s went in for mass of M1 and M2 respectively, and the velocities went in that we know, and the velocity we don't know is missing, and it's just algebra at that point to solve for the combined velocity. Right? So a bunch of numbers there, multiply and subtract and so on. Eventually, I have it all worked out here. I don't always show all the steps in grade 12 here, but dividing both sides and you get your velocity of 2.057, blah, blah, blah. So if we're going and looking back, like, oh, they've only given us 2 significant digits, we're going to keep it as 2.1. Technically, I would argue that should be 2.0, actually. I'm going to change that. I went with 2.1 because that's what the textbook version had, but this is the even rule, right? Because it's a 0.5. If it was a 2.06, we'd certainly say 2.1, but 2.05, technically I should round to 2.0. So we don't round up more often than we round down. Okay, so that's what I'm hoping you would do. Just plug numbers in, solve it out, right? And like we talked about before, the textbooks don't like to have all these numbers posted in here. So I feel like that's probably why they do this. But they solve for V1 prime and then, plug numbers in, and then the calculations just magically pump out the 2.1 answer. So therefore, blah, 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 right? Therefore, the combined velocity of them is 2.1 meters per second, and it's positive still. Let's say, and why is that? They're saying in the direction of the initial velocity. You can tell because this became a positive here in both cases. And so, if we called the direction of, what do we have here? The two, right? We had this direction was listed as the positive one. And then this was the backwards direction, the negative, right? So it's in the initial direction of the full bag, I guess, the 108 kilogram person. So just to watch for the direction meaning in your answer. Any questions about that? Okay. What do they have here? Yeah, the idea of masses joined together, which we've obviously already done thoroughly, so we're good to go. All right, so this actually leads us into the next thing, right? This idea of elastic collisions. So, the good old Newton's cradle. Do I have a video here? I can probably just Google one here easily enough. Newton's. Let's see what we got on YouTube for Newton's cradle. Oh, it's a big one. Let's see. Sound for this. Get this out of the way. And I need to unmute my sound. Okay. Here we go. Skipping ahead maybe a little bit. Holy. Lots of lead up here. All right, so the first thing you do when you grab this thing is you grab one ball, of course, and you let it go. And not too surprisingly, that happens, right? The one that some people find surprising is maybe this one, right? Where the person takes two balls out to one side. Okay, so in a second here, if he shows them pulling, there we go. So two, so I pause, predict what's gonna happen, right? Well, we saw that two go flying out, but the question I'm gonna be asking is like, why can't one go with like twice the velocity? Any thoughts on that? Why one can't go with twice the velocity instead? So many people think that the way this thing behaves demonstrates a conservation of momentum, right? So of course, momentum is conserved. It's totally true that momentum is conserved, right? All things conserve momentum. It's always conserved. Conservation of momentum doesn't actually fully predict what we see here. Okay, so particularly in this video. This is actually a good video. I'm gonna be linking this one in there for you, and maybe getting a copy of it. Don't tell anybody. Yeah. So any ideas? Like, could the one go with twice the speed instead? And really, you see what happens here. The two go out with that same speed. And then I'm assuming the video probably goes on and play around with other things, like you take one from this side and two from that side. It's kind of fun to do. Did they do that? Oh, I do one from each side. That's kind of fun to see. And then eventually, hopefully they do, yeah, there we go. That's the one. Oh, no, two from both sides. You can do two from one side and one from the other. I hope they do it. You can do anything you want, really, of course, but here we go. Three from one side. There we go. So let's, if you didn't get a chance to quite see what happened there. Give it a minute here. Oops, pause. So we got three here, two there. What happens? The other ones were kind of obvious, right? Like one bouncing against one, one bounces out each way, or two bouncing from each side, they bounce out. This one's a little weirder to kind of picture what's going to happen. I think you guys are shy on keying the microphone, but did anybody see what happened? Or yes. Go ahead, sorry.
Does the middle one alternate?
Yeah, I think that would be a good way to word it, right? So basically the three, the way I see it is the three keeps going and then the two almost keeps going. And so you're right, the middle one alternates. It's kind of two different ways of describing it, but yeah, watch, it's kind of neat. Right, so the middle one definitely, I like how you said that actually, it kind of alternates. So what I'm seeing is 3 here going in and 3 continuing to go out, along with 2 coming in from the right and 2 continuing to go out. So it's just kind of, it's neat, right? That's why people like this little device called the Newton's cradle, because it's just kind of fun to play with. So maybe play the video some more there later if you want to see what other fun things you can do with it. So what happens if 2 go in? Obviously, we see that 2 go out with the same velocity, right? So my question was, well, why can't 1 go out with twice the velocity sometimes? You know, would momentum not be conserved? Is that why it can't, or it doesn't happen, right? So is it not happening because of that? Well, let's look at momentum conservation. Okay, so would momentum be conserved if 1 of them went out with twice the velocity? Hopefully you can see why we looked at stuff before with, like, remember we looked at, you know, the electric force was KQQ over R squared. And we said things like, what happens if you get like 3 times the distance? And what happens if you have like twice the charge, right? It's good to be able to visualize what's going to happen and put things in the way I've done here, right? So the idea of, oh, I want to think about twice the velocity, then I'm just going to make it be 2v1, right? So that's where that was leading to, just being able to work with concepts. Notice the masses are all the same, so they can actually just completely cancel out. And so we basically end up with this new equation where we have v plus v equals 2v, because all the velocities are the same, as we've said, right? We're going to go with twice that v1 velocity or whatever. And so we end up with a statement from conservation of momentum that 2v equals 2v, which is clearly true. And so momentum would be conserved if 1 went out with twice the velocity, right? So what we're saying there is that, you know, the way this thing clearly it behaves a certain way, right? 1 doesn't go out with twice the velocity, instead 2 keep going, right there, right? 2 keep going. Not just 1 with double the velocity, and we can't say, ooh, that's because of momentum. So what is it because of? If it's not because of momentum, what is it because of? Any ideas? So it's because, as a buzzword, it's because it's an elastic collision. What did I mention previously about elastic collisions? When I talked about the objects sticking together, what was the issue? They're completely inelastic because, I just have to find where the heck that was, right here.
It go out with any kinetic energy.
Yeah, it has to do with energy. That's right. Right. So this idea, if it's completely inelastic, then that means that like none of the energy comes back from the squishing of the material. Whereas with this, we're talking about a special case where they say all. I think it's safer to say like almost all. I don't know, but basically it's because energy is being conserved, or darn close. So conservation momentum doesn't explain it. But there's another physics principle at play here, which is energy, conservation of kinetic energy. Okay, so if we look at that, when we look at conservation of kinetic energy, that would mean that all of the energy stored during the collision comes back to kinetic. And in full disclosure, of course, we're saying like almost all of it. But it's just, if things are really springy, then the energy comes back out really well. And so we call them elastic collisions. You know, in an ideal case, we'd say they're like completely elastic, meaning all the energy comes back out. But of course, we know it's not a perfect world, right? So it's interesting, actually. Like I wonder how elastic it has to be, you know, in order for this to for it to happen. I don't know how that works. I think you'd always get 2 going out. I think it just that the energy would just dissipate quicker, if that makes sense. They'd slow down quicker, right? Because clearly in the video you see them like going, but they start to slow down over time in a couple different spots we saw. And that's just because we're losing energy gradually rather than all at once during a collision. That's the best way to put this, actually, thinking about it, right? Obviously we're going to lose some energy to friction and whatnot over time, but it's a super gradual loss rather than like a whole bunch of energy getting transferred to heat during the collision. So let's summarize the types of collisions that we've talked about. We're just introducing elastic collisions right now. So momentum and kinetic energy are both conserved. Might want to get rid of the word completely there, but they're both conserved, right? As the objects rebound from one another. So what we're saying for that one, the key was that kinetic energy stored, right, comes back to, gets stored as elastic potential and then comes back to kinetic. Okay. And it's a little too strong to have this all and completely, but the idea is we're not losing a whole bunch all at once at any rate. So maybe that's a little too strong, right? You could add, although you do lose some to friction and heat, of course, gradually. Previously we saw partially elastic collisions, or actually, I guess it's all kind of part of the right what we're doing right now. But momentum is conserved, but kinetic energy is not completely conserved. So you could have like not all of the energies coming back out to kinetic. And then recently we saw the completely inelastic. So this is sort of officially talking about it. What's happening with energy in that one? So we know momentum is conserved, but much of the kinetic energy is lost other forms. And they're sticking together. So what would the blue state paragraph be? Any guesses? Blue sentence, whatever.
That nothing does?
Yeah, exactly. Nothing comes back out, right? So none of the kinetic energy stored comes back. It all just gets dissipated away in the objects as heat. Sometimes teachers would just say, none of it comes back. It all gets quote unquote lost in the collision. And it's a little bit dangerous to say that, right? We should be a little more aware of where that energy really goes. It's not like it goes poof magically out of existence or anything. So those are our types of collisions that we're kind of visualizing. I'm not sure, to be honest, I'm not sure what this one would look like. Like if we had a Newton's cradle version with partially elastic collisions or partially inelastic and so on, I'm not certain it would behave a ton different. You'd almost have to make a Newton's cradle with tennis balls or something, and I suspect it would behave the same way. It would just dissipate quicker. I don't know. I'm not sure. So this is completely an example of video of elastic and completely inelastic collisions. Let me just quick pause here because I had a note there to myself saying, yeah, after the video, we're going to look at that. All right. I just want to make sure I was following my plan here. All right. So that is an elastic collision. You can see like energy was stored and came back out. And, I think it's probably because it's a big spring going in and there's some friction and so on, you'd probably consider this one partially inelastic, right? A heck of a lot of energy comes back out, but there's more efficient ways. We're using the spring plunger here. If I turned around and used the magnetic repulsion, which you got to play with earlier in the year or last year, for some of you, it's even less friction, right? And so it'd be closer to truly completely elastic. So I think what we saw there just now was, what we'd consider to be a partially inelastic. Now keep watching. So partial inelastic, and then it's like, ooh, what about that one, right? In the end, I can't really control if these spring plungers do this, but I was so happy when I got it on video at least, because one semester I was bouncing the car back and forth, I think probably for 10 minutes straight, trying to get it to actually catch, because there's no way to control it. Sometimes it does, sometimes it doesn't. And the first time I saw it do it, I immediately thought, oh, I have to try and use that. I can use that in an inelastic collision example later on when I'm teaching that topic in grade 12, right? So of course I went to work trying to make the videos and whatnot. But yeah, so you can see as the car bounces, right? Kinetic energy stored in the spring, and then most of it comes back out in the first 2 times. But then on that third bounce, the spring compresses and gets stuck, and that leaves all that kinetic energy stored as elastic energy. So that's a video that very much shows completely inelastic collisions. Okay. Another video would be easy. It would be just like take a ball of Play-Doh and throw it at a brick wall. Or better if you threw 2 balls of Play-Doh at each other, I guess, and they stuck together and went to, just stopped in a lump. It's still completely inelastic either way. Any questions about that? Okay. I think that shows what we're talking about well there. If you want more, this one just describes just a it's just a paragraph from the online course actually that describes what we just did. So I'll leave that for you to look at if you feel like it. But something fun here to think about. In 124, I have these what I call happy and unhappy balls. And so I'll show you a video of happy and unhappy from room 124 back in the day. So there's happy and unhappy. You can see why they're called happy and unhappy. Right? Got these two black balls. One bounces, one barely bounces at all. Right? So we've got happy and unhappy. They're affectionately called. So the one on the right has a mostly elastic collision, bounces well. The one on the left has a mostly inelastic collision. If you bounce them over and over and over again, I think, if you did careful enough measurements, I think you'd be able to measure the temperature of the two balls. Which one do you think would be the warmest after bouncing it for an hour straight?
The happy one.
Well, no, sorry, but you want to think the one that's absorbing the most energy, right? So it's the unhappy comes down and slams to the table and stops. All of that energy goes into the ball and stays there, whereas the happy one bounces, and so the energy comes back out to gravitational potential, right? So it's the one where the idea of that energy gets stored or in that ball. But don't feel bad. I appreciate the mic key and the risk taking. It's all good. Makes things more interesting if people are thinking about it and trying. So this is a video to do with that I found recently that's pretty good. This is the Action Lab guy. I think I've shown him before. He has like the coolest job in the world, I'm thinking. Although it's not very interactive. I like being able to interact with the class as I'm teaching stuff. He's teaching the world's physics through cool videos, but not interacting. First is ad from iPhone and Bell.
Hey everybody, today I'm going to be showing you the world's least bouncy ball made of polynorbornene. Now these balls...
Polynorbornene. I don't know the background of this, so it's actually kind of cool for me to hear like, oh, he actually goes further into this and explains why one's bouncy and one isn't. So it's actually kind of neat.
They look very similar. They're both completely solid, about the same density. They weigh about the same, but this one's made of neoprene and this one's made of polynorbornene. So on the macro scale, they look about the same, but on the molecular scale, they're quite different.
So the macro scale, looking at them from, like looking at the overall size and whatever, the bouncy one is always a little shinier, just because of the luster physical properties of that material. But we know the bounciness. Let me show you what
they look like. So if you could zoom in on both of these balls, you'd zoom in on the neoprene and you'd find these long chains of carbons with a few chlorine atoms here.
So this is a neat little crossover between a physics thing we're doing and a chemistry thing. We're talking about the molecular buildup and makeup of these rubbers, which is kind of neat.
And if you could zoom in on this polynorbornene here, you'd zoom in and you'd find also these long chains, but you kind of have these house-like structures of carbons in here. So you can imagine if you were to hit both of these molecules, you can imagine this top one, it kind of looks more like a spring. It could kind of compress and then push back on you, so it would be a little bit more elastic. But this polynorbornene here, because of these 5-membered carbon rings here, as you push on it, it would kind of restrict the movement. But you're still putting energy into it, and so as opposed to compressing and then pushing back on you, what it does is just cause those molecules to vibrate a little faster.
Which we know, molecules vibrating faster is heat, right? And so that's why the unhappy ball, the polynorbornene one, would get warmer.
Twist and turn a little bit more. And all that does is increase the temperature. So as you hit both of these, this one pushes back on you, and this one starts moving faster. And so what that means is this one rises,
vibrating faster, getting warmer, in other words.
In temperature, and this one doesn't change temperature that much.
Gotcha.
And so one of them is bouncy, one of them doesn't bounce but increases in temperature. And that's exactly what we see when we drop these. So let me show you what happens when we drop both of these on a hard surface. You'll see that this one bounces almost to the same height, and then this one just kind of plops on the ground and doesn't do anything. It absorbs almost all of the shock and it goes into increasing the internal temperature instead. And then after we see what happens at room temperature, we'll see what happens if we actually increase the temperature of the balls. Does the elasticity of both materials stay the same or change? Okay, now see if you can guess which one is the polynorbornene and which one is the neoprene. Okay, 3, 2, 1. This one just plops on the ground and nothing happens. No movement whatsoever. Okay, let's try it again. Look at this. 3, 2, 1. It doesn't even bounce whatsoever. It just hits the ground and stops.
I think I'd get along with this guy. What else does he do? I'm not sure if he does much more here.
What happens if we warm both of these up? So I'm going to warm both of
Yeah, so he goes further into like what happens if. You're welcome to check that out, but it certainly accomplished the part I wanted. The idea of energy stored in a collision and then released back out is kind of a neat result too. He did the world's bounciest surface, and I haven't actually tried this personally yet. I was planning on trying, and now we're not in room 124 anymore.
I don't love that as I age, I could develop
Hang on here.
issues. New Colgate renewal.
Skip ads.
Hey everybody, today I'm going to be showing you one of the world's bounciest surfaces. And also,
So
I'd like to
he
thank
talks a bit about the idea of the energy stored and so on. So how much you've been thinking about the idea of elastic collisions when he's saying this, right? The energy stored and then released, and that's why it's able to bounce so well.
KiwiCo for sponsoring this video. I'll tell you more about them later on. One quantitative way that we can measure bounciness is through something called the coefficient of restitution. Now, the coefficient of restitution is just the ratio of the velocity of the ball after the collision compared to before the collision. So, for example, a coefficient of restitution of 0 would look like this.
Splat.
And then a coefficient of restitution of 1 would mean a perfectly elastic collision. So it has the same velocity after it hit something as before it hit that thing. And then you could even get a coefficient of restitution of greater than 1. That means that something's exploding after a collision. Now that sounds silly, but that actually used to happen with billiard balls.
So coefficient of restitution of greater than 1, meaning you drop a ball from like 1 meter and it bounces to like 1.5 meters, right? It releases energy. And he said it's kind of silly to talk about that, except it actually used to happen with billiard balls that had a compound in them that sometimes would have a little bit of an explosion. I hadn't heard about this, but apparently this is something that people know about, but I'll let it go here.
Balls that had nitrocellulose in them, sometimes they would hit and have a small explosion afterwards, so it would result in a greater velocity than the impact velocity. The coefficient of restitution isn't completely dependent on the material. It can actually depend on the shape of the material and how the collision happens as well. So what's most important is that when you want something to bounce high, you want all of the kinetic energy that thing had to be returned to it after the collision.
And that's exactly why I'm showing this video, right? It gets stored according to the Hooke's law and the elastic potential energy, and then gets released back to kinetic. And if you're releasing a ton of it back to kinetic, then it's going to bounce for a long time.
So whatever you throw against a wall or bounce on a floor, you want all of that kinetic energy that it had right when it struck the object to be returned but in the opposite direction. Now, ways that you can lose that kinetic energy is through deformation. So whenever something deforms, for example, when you throw a ball against a wall, it slightly deforms, and that causes some energy to go into heating the object instead of returning it to the kinetic energy, pushing it back the other direction. And also a sound is made when it hits an object. So you lose energy through heating it up through deformation and also through sound. Okay, so I have my super bouncy surface here. I'm going to drop a blue steel ball on it, and let's see how long it
So
actually
I believe
bounces.
that's just a balloon stretched over like a bowl or a cup or something. I could try it at some point.
1.
Clearly, a lot of the kinetic energy, or stored potential energy, I should say, elastic potential energy, is coming back to kinetic.
Whoa.
If it's able to bounce, you can even hear it. It actually starts to mess with the frame rates of the video. It starts to look like it's suspended once in a while. Now it's just kind of
Even though it
jiggling
looks
back
like
and forth
it's not
slow.
bouncing anymore, you can still see it just vibrating back and forth.
Isn't that amazing? He does another one.
It
A
almost
bigger
bounced
ball.
up to the same height in which I dropped it.
Yeah.
So look how high it came up to my hand. It's almost like it had 100% coefficient of restitution.
Pretty close. Yeah.
Now let's try even just dropping a ping pong ball on it.
So anyways, if he
Stretch
goes
it
with
over a
heavier
cup,
ones,
and it makes this extremely bouncy
he shows how to
surface.
do it there at the
So
balloon.
why does this?
Anyways, idea of energy being stored and coming back out. I got a little carried away there, but it's all good. Oh yeah, just how inelastic are things sometimes. You probably remember hitting the two metal spheres together with the paper, showing that that the energy is going to heat. When I was talking about conservation of energy in that in grade, I might have even been grade 9 or 10 science, where I tend to show that more often. Anyways, it burns a hole in the paper, so that's the energy that's getting transferred, or lost, as you'd say, quote unquote, lost to other forms, right? Actually burn hole in holes in paper. Anyways, so the math, the way we have to calculate this out is we have to look at conservation of momentum and conservation of kinetic energy. So delta P, the change in momentum, is 0, and delta EK, the change in kinetic energy, is 0. We have to do both of those. So it's two sets of equations. You've got an M1V1 plus M2V2 equals M1V1 prime plus M2V2 prime. And we also are going to have a 1/2 M1V1 squared plus 1/2 M2V2 squared plus equals 1/2 M1V1 prime squared plus 1/2 M2V2 prime squared, right? We say it that way, but then you're quickly going to be like, oh, wait, there's a 1/2 everywhere, so no sense wasting battery power dividing by a half all the time. I can just cancel all those out, and so on. I didn't actually show it here. I'm going to when I actually officially do this page, when I finish it up, once I have my pen in my hand. So anyways, if we had, so here's the question, instead of a paragraph of just giving you the given information, if we had M1, mass number 1 is 1 kilogram, mass number 2 is 2 kilograms, and V1 is 10. In the past, I said, this is recall actually here, right? In the past, I said, ooh, I'd have to give you one of those velocities, right? Like if I gave you this is -4, then we can calculate out that the corresponding would be 7, right? Because we have, and I said at the time, soon we'll have, we'll see another value or another concept I maybe should have said that's conserved, right? And so we'll be able to calculate both of those final velocities. So today is that soon day. Yeah, so given one of the final velocities we could determine, but I'll get rid of that page. Because, oh, wait now. I don't know what I did there. I think I just hit the arrow, went up. But that's what we were thinking about at the time, right? Is given one of those, we're able to get the other one since momentum is conserved. But this is what we're focusing on now, the idea of being given this extra information. So first of all, I want to check, was this collision elastic? What does that mean? If I ask, was that collision as is? If it went to, it became a -4 and a 7, was that elastic? Well, let's look, right? What that means is that was the kinetic energy conserved. This used to fit onto this page, I think. Let me squeeze that down and I'll read it with you here. It smart notebook a minute to recover from that calculation. So what I'm saying there is it's likely wasn't elastic because I randomly picked a final velocity of the first card, knowing I could calculate what the corresponding velocity would be because of conservation of momentum, right? It's likely that I didn't pick the particular value pair, the particular pair of values that satisfies both momentum and kinetic energy, right? But I honestly, when I was writing this page out, planning this lesson, I didn't know. So I was just checking to see, right? So plug all the numbers in. And of course, like I said, calculation wise, you don't need to worry about the 1/2s. So you could just get rid of all of those right off the bat and simplify your calculations a little bit. But we've got 10 squareds, 100. So I could just say 100 plus 0. I think I have it as 50 there, but I could have had it as 100. I just wanted to show you that you could do that. And then here you'd have the 16 and the 49 times 2 and so on, right? So either way, you can either, use the half like I did actually here because I didn't think of it at the time, or you can cancel it out. Anyway, so we're getting a result here, right? So this 7, remember this was just calculated based on conservation of momentum only. Was this an elastic collision? Based on the results there. We had 50 joules of kinetic energy at the start, and we have 57 joules of kinetic energy at the end. What does that tell you about whether this is elastic or not?
That it is elastic.
It's actually even better than elastic though, isn't it? Elastic would be, so if it's elastic, let's go here. If it was elastic, then we'd have 50 equals 50, right? We'd have the same amount of energy before and after, or super close. 50 equals 49.9, you know, and it's close enough that it behaves the way we think, right? So that's elastic. This one's weird, okay? So I actually put a note in my other lesson, and I decided to show both of them because we talked about just a second ago the idea of the coefficient of restitution of greater than 1. You can actually release energy if a pool table ball explodes during a collision. You can actually get them going fast, you know, more kinetic energy afterwards. That's what this one would have had to have been. Okay, energy must have been released is what I was hoping we're going to see there. We've got more energy at the start, at the end than we did at the start, right? So we actually have, you know, 7 more joules after the collision. Sorry for the scribbly writing. I just don't have my screen flipped around so that I can write better because I don't have a keyboard. Anyways, so does that make sense? It shows we got more energy released afterwards, right? So what I did is I went back and I redid this equation or this collision here, so that basically, you know, if I said, well, what if this velocity was, right, the one velocity was -1, right, instead of being -4. So because I chose -4 here originally, just knowing I could calculate whatever, I could use whatever I want there. In the corresponding V2, I can just calculate what it would be in order for momentum to be conserved, right? But it turned out that this had to be a situation where energy was released, which is totally possible, but just not with just simple balls colliding, right? You'd have to have like spring-loaded balls colliding somehow, or exploding balls colliding. Anyway, so if I chose the -1, then we calculated in the previous lesson, right? We calculated that 5.5 was that corresponding momentum, okay? So in a more realistic case here, a -1 corresponds to a 5.5. When I calculate out the energies, I end up with a more common answer here of, oh, we had 50 joules of energy. We ended up with only 30.75. So we've lost some energy. What did we lose it to? Heat, right? So some of the energy stored during the collision is not returned to EK, so we've lost some to heat, etc. Heat, sound, you know, whatever. Make sense? So that was just to check to see if the way we calculated previously with either a -1 or a -4 for one of them, giving the, you know, we calculate the corresponding velocities with conservation of momentum, we're checking to see if those happen to be elastic, which it was very likely they weren't. So now the new stuff we're really using here, using the power of this, is what would the final velocities, we're calculating both of them this time, right? What would they be if the collision is elastic, perfectly elastic? So notice I'm giving you the same initial stuff, right? But I'm not picking some final velocity for V1 and then calculating the corresponding one. We're actually going to calculate both of them, okay? So follow along here. We have the two concepts simultaneously, really. I'll go through the momentum one first, but I need you to think of the idea that we're talking about conservation of momentum, but we're also talking about conservation of kinetic energy, and that'll help us through this question. So delta P equals 0 or initial equals final, either way. So that's just your usual momentum equation. M1 V1 plus M2 V2 equals M1 V1 prime plus M2 V2 prime. More you practice it, the better you get it. Saying it and writing it down and so on, right? It becomes less onerous. It doesn't seem as crazy after you practice it for a bit. So we start to plug in numbers. So I've got M1 is 1, and the V1 is 10, and the 2 kilograms, and the initial one was I didn't write it in there, but it was colliding. It was colliding with a stationary M2, right? So I needed to have V2 equals 0 was given as well. me just write that in there and just correct just the out of context here. It wasn't obvious, but that's what was happening in all of these cases. So we've got the 1 kilogram with the unknown final velocity of mass 1, and we've got the 2 kilogram with the unknown velocity, final velocity of V2. So we end up with this this equation here, where we're like, oh, okay, so we're ending up with 10 equals V1 prime plus 2 V2 prime, right? And that equation, you can tell you can't solve because you have 2 unknowns, right? But luckily, there's this other concept we're working with. Okay, I'll just maybe pause for a little bit there so you can digest and think about things, write things down, ask questions. Okay, so it's not super obvious yet what we're maybe at the stage, if I didn't show the 1 and so on, right? It might not be super obvious. You might feel like you're stuck, like, oh, I can't solve. What do I do? What do I do? You know, and you keep trying, obviously, right? So you think, oh, wait, there's this other concept. Kinetic energy is conserved as well. So here I remember to actually cancel out the halves and save myself a little bit of trouble. But this gives us a different equation. It gives us a 10 squared, you know, and it's, you know, just slightly different because of the squares, right? So it gives us 100 equals a V1 prime squared plus a 2V2 prime squared. Okay, so hopefully you are starting to have the experience of joy, if you will, or relief, maybe, if you see 2 equations with 2 unknowns. Remember, I kept saying, I said it back in grade 10, I said it again in grade 11, and I'll say it again now, right? This in grade 10 was new hard stuff. 2 equations, 2 unknowns, oh my goodness, substitution, elimination, oh, that's lots of work. But now you're gonna have to start to get that to just be something you're good at doing. And now, in this case, it allows us to solve a grade 12 university level physics question. We'd be like, sweet, all I have to do is do some grade 10 work, and that gives me the answer for grade 12. That's something I need to be able to do and have it not be a bad thing, right? So notice that it's 2 equations, 2 unknowns, and you can just do substitution and make it happen. So I'm going to solve for V1 from this one, obviously, because it's a little easier, right? Instead of solving for V2, solve for V1. So just subtract V2 prime from both sides. I'm solving for V1 prime, I should say. The final velocity of mass 1. So if I have what V1 prime is, right there, right? That's what it is. I can put that into here. So that's my substitution happening. Anybody need that page a little bit?
Just a minute longer, please. Sorry.
No problem at all. Just let me know when you're ready. And then everybody else can key their mic too if they need more time. Right on. Thank you. Okay. Like I said, everybody can key their mic if they need, but I appreciate you helping me pace things here. So we're putting equation 3 into equation 2. That's a nice way to sort of organize your thoughts here, right? So, oh, call that equation 1, call it equation 2, and then a new one's equation 3 here. And we're putting that into equation 2, so it's very obvious what I've done. So there it is. And I'm making sure to show very, very carefully what happens here. Specifically, I might want to point out that this underlined red part here does not become 100 minus 4 V2 prime squared. Okay, emphasizing here with the red, if you have A minus B squared, that is not equal to A squared minus B squared. That is a very common mistake that people make. You know, if I wasn't a math teacher myself, I'd blame it on the math teachers. But I know for sure I teach this as best I can, yet people still do it. And it's just a human nature thing, of course, right? But you hear that sometimes. Some teachers be like, "Oh, who'd you have last year as a teacher," or whatever. Try to, you know, and then it's funny if it's like, actually, I had you. But anyways, so we know that we have to square a binomial, right? It's like, you know, all done here. So think of, I'll help you a little bit more even. Instead, you'd have your A minus B times an A minus B. Instead, it does equal this. And so if you really want to think it through, it's an A times both parts there and the minus B times both parts here, right? Most people get to the point where they can start to just realize that the answer becomes the first thing squared, A times A. The first thing times that is a minus AB, but then we have another minus AB. And so that's why I'm writing it as a minus 2 AB here, right? You get one from each part. So you've got this one, let me just make sure I'm doing this right here. So the A times the minus B and the A times the minus B. So those two parts there become that. And then finally here we have the, the minus B squared, right? So it's a little awkward because I have a minus in this case, but I'm just trying to show you what we really have. But notice how minus B squared is going to give you a positive B squared, right? So long story short here, or maybe short story long, you end up with this. So I'm showing you here, we got the 10 squared. We've got the first times the second times 2, which comes from this logic. So we got the 2 times the 10 times the minus 2 v2 prime. And then we have the negative 2 v2 prime squared. Okay. Tons of math help analysis there to try and get your skills reviewed, so you can get correct answers in real life, i.e. physics questions, describing real life things. Yeah, so we end up with that. Notice some happy algebra here. We have a 100 equals a 100 plus a bunch of other stuff. You're like, ooh, I can just subtract 100 from both sides, make those go away. I had written in there that always happens, but I'm not clear exactly in my mind as to, sometimes it happens, sometimes it doesn't, apparently, because there was a homework solution where I was like, it didn't cancel out. And I was like, I think it's, in this case, if you have the second velocity is 0, I'm pretty sure that I can say at this point that if the second velocity, the velocity of the second object was 0, then they cancel out. But if it wasn't, then they don't. So don't expect it always will, but if it does happen, you take advantage of it, right? But so that simplifies algebraically to be that. What I've done, of course, is I've taken the 2v squared from this part of the equation and the resulting 4v2 prime squared from that part and combined them. So there it is, collecting like terms. And the minus 4dv2 prime is there. So again, because we have this second velocity, velocity of the second object, I should say, is 0, we can just common factor out. It's a quadratic, but it's a simple quadratic where we don't have a constant term, so we can actually just solve directly using algebra. If you do have a constant term, which you will in some of the questions, you have to use the quadratic formula. Okay, so we're talking about these two factors, v2 prime times this thing, 6v2 prime take away 40. That has to equal 0 because the 100 became 0 by subtracting 100 from both sides, right? I could show that if you needed it. Take away 100, take away 100, right? These two sides are clearly still equal to each other because they're both different by the same amount. They were the same, and so they're still the same. It's the logic of it. Yeah, so we're saying, well, that would be true if v2 prime is equal to 0, or if this factor is equal to 0. So think about what this would mean. v2 prime would be 0. Be like, okay, we're talking about a collision where mass 1 comes in with 10 meters per second and hits a stationary object. Okay, can that object stay stationary if it's an elastic collision and so on? Well, no, because it can't have the same velocity it started with. It's going to undergo some forces, right? And so it's going to accelerate somewhat. It's going to have a different velocity in the end. So basically, this one's just an illogical answer that the math says mathematically is possible based on the math relationship, but we're saying based on the physics relationship, you can't have a final velocity the same as your starting velocity if you've undergone a collision, if you've undergone some accelerations. So this one helps us get our answer. We can say 0 equals that 6v2 prime take away 40 add 40 to both sides, divide both sides by 6, and we're getting 6.6 repeated, or to two significant digits, 6.7. So we have found out the speed that the second one would actually have if it's an elastic collision, right? And then we can figure out the velocity the first one would have as well. We're actually calculating both of them. So for the first velocity, obviously you'd use equation 3, if you will, right? This equation here that we numbered, v1 prime equals. I might as well use that one instead of one of these ones and having to solve for v1. I've already done the work to solve for v1. So use the v1 equation that we already worked with, plug numbers in, and get that it would have a negative 3.3. So in other words, 3.3 meters per second back. Okay, so we figured out both the velocities this time. We didn't have to pick one and then solve what the other one would be. We solved for this particular pair. I should emphasize here, this is a V2 prime. I'm gonna go purple because it's my emphasis color here. This one and this one, this is a pair of velocities, right? That satisfies conservation of momentum and conservation of kinetic energy. Okay, so we saw two examples previously where we saw pairs of velocities that satisfy conservation of momentum, but they didn't satisfy kinetic energy conservation. So in other words, they weren't elastic collisions. So just as a little sanity check here, you can check to see what the kinetic energy is before and after, and quickly the calculations lead to 50 is at the beginning and the end, and same energy at the end as you started with. Okay, so that's new. Just to do a quick recap, remember you're working with the conservation of momentum equation and the conservation of kinetic energy equation, right? It leads to a two variable equation from both of them. You combine them, good old substitution elimination style. It's always substitution in life, typically, almost always substitution in life, even though in math, everybody likes elimination. But when you're actually using it to do something, substitution tends to be the way. They're not just both linear equations and they're not all lined up and so on. Okay. Questions? Okay. All right. So anybody need that page a little more? No one's keen. There might say they do, but I always like to offer.
I guess we're okay.
Fair enough. All right, so this one is just another one all worked out. I will reveal those boxes and let you look through it as another example. I want to focus on something cooler than that. Okay, cooler being used loosely in the context of a physics class, of course. Lee reminded me or pointed out that I forgot to reveal those, but that's the thing. You see it here, and you get your momentum and your kinetic energy, and you substitute in, you solve, and you get answers. But we have a situation where we've got a ball coming in at 5 and a ball coming in at 4, and then we're like asking what are the final speeds going to be for both of them? If it's an elastic collision, what are the final speeds for both of them going to be? And this page absolutely works it all out. And so we needed the quadratic formula with this one, so it'd be a good one for you to things out. And the same idea of, could this final velocity be, there's analysis there about make sure to do this, okay? Because the idea of, right here, it's the same analysis, right? What the final velocity can't be the same as what you started with. That's the same thing. And then I have also checked the other velocity, and they'd actually physically have to go through each other in order for the other velocity or from the quadratic formula to be the result. This one has a video to go along with it, so it'd be a good one for you to do and then see the video. Okay, but it is obviously just extra practice. And there's another one actually, another extra practice worked out. So what I do want to focus on here is a cool example, and I was excited to show you this because it's kind of neat. So if you've been watching baseball, like I have been, but if you've ever watched any kind of sport, they have stats, right? They tell you about things. And so they're saying here, like a home run can leave a bat at like 110 miles per hour. So Vladimir Guerrero Jr., for example, is his exit velocity. They call it the exit velo in baseball. So any baseball fans are all over this right now. So Vladimir Guerrero's velo is what? Anybody know? What's his exit velocity often? He's top in the league, highest exit velocity. Often he is well above, or what is some numbers? Anyways, he's above 110 more than anybody else in the league. He hits like 115, 117 exit velocity. Anyway, so the ball leaves the bat with that kind of velocity. A fastball coming in can be like 92, 93, 98, whatever, right? But an average fastball may be about 92. The mass of the baseball is 145 grams. The mass of the bat's 1 kilogram. The center of mass, so the speed of the bat, and they're saying, like, basically they're trying to get you to picture the bat as being basically an object that collides with the ball, right? So the barrel of the bat, I guess I have to move down to the barrel of the bat area here. They don't have it lined up. The barrel's more about there, I think, right? But anyways, the collision here, you want to think of it as a 1 kilogram object colliding with a 145 gram, 0.145 kilogram object. Okay, so this calculation is just, conservation of momentum. They're saying if this is the final velocity of the what is that one there? V1's the bat or the ball? V1's the ball. So they're saying that the final velocity of the ball is the 49. Just have to get myself straight here. Yeah, that's the 49 final velocity of the ball. The initial velocity of the ball was 41 the other way, so see it's a minus. And then they said the bat was going 22. They're asking here a little bit of a weird question. They're asking, what's the speed of the bat after hitting the ball? Okay. And we've talked before about the idea of like following through a bat. When you see a good baseball player, they swing through the ball. The bat is still going forward even after they hit the ball. When a little kid trying to learn how to hits a ball, the bat ricochets backwards, and the ball doesn't go nearly as far. Okay, so this is someone who's swinging through. So we're expecting this velocity to be forward still. Okay, so we'll run the numbers. This is a review, right? So I'm just going to show it. This is just conservation of momentum, right? Numbers go in, boom, boom, boom. You can calculate out the speed of the bat is still forward, but it's around 9 meters per second instead of, right? And in terms of two significant digits, 9 meters per second. So the bat slows down, but it's still going forward. He swung. He swings through the ball. Okay, when you do this. So if you've been following baseball current events from last year and this year, this will be good for you. If not, you can still follow along, of course. But question is, okay, actually, we're not quite at that one yet. We'll get there. What if the collision, or was the collision, sorry, elastic? Okay, so that's from today's stuff. Was the collision elastic? In other words, was kinetic energy conserved? So this is entirety, just plug numbers in. You're like, boom, boom, just put the numbers in, see what your kinetic energy is before and after, and see what you get. So the numbers, based on where I got this from, there's actually a whole PDF I've saved. It's like the physics of baseball. So they had this example all, there to work out, whatever. And so I calculated here that the kinetic energy before and after is quite a bit smaller afterwards. So you can tell you've lost a lot of energy. You've lost it to heat, you've lost it to sound. The announcers know instantly if it's a home run because of the sound, right? As soon as a bat hits a ball, if it's a home run, they can tell the sound of it, they can tell, okay? So some energy is going to sound. The majority of it's, of course, going to heat and deformation of the ball and so on, right? Like they don't reuse baseballs after a home run because the ball's like slightly crushed inside, I'm sure, right? But anyways, so that energy goes to crushing the ball and heating it up and sound and so on. Kinetic energy, what I have here, would be even smaller if the bat breaks. Yeah, that's another example. You see a broken bat, often ends up actually being a single because the ball lands shorter than they were anticipating. So the outfielder's out too far, but you can picture some energy goes into breaking the bat, right? And so you end up with less velocity. So you have the force, that is applied is less, right? So because the bat's breaking, this is actually linking back to the impulse stuff. right? Because the bat breaks, you end up with the collision lasting longer, which means the contact force to change the momentum is less. So you have less force, you have less acceleration, you have less velocity. So there's multiple explanations there as to why, if the bat breaks, the ball doesn't go as far, if it wasn't obvious already. But certainly the idea of the bat absorbs a ton of the energy because it breaking, like the physical energy of breaking it is absorbed from the velocities. And then our analysis of conservation of momentum, the momentum change, I should say, actually, because that object's momentum is changing overall, the momentum is conserved, of course, but for that object, it certainly does change. Less force means less acceleration. So we're confirming that certainly it wasn't elastic, right? So the question is, if the Houston Astros, okay, the cheaters that they are, right, decided they wanted to use a very springy baseball because they think it would give them an advantage, so they go out and they manufacture some super elastic baseballs and manage to get them in the umpire's hands. Obviously, it's very controlled in baseball, right? The teams don't supply their own balls. But in football, of course, there's a team that got away with this for a while, right? With different inflation levels and so on. So what would happen if the Houston Astros managed to get a bucket of, or a big box of very elastic baseballs in the umpire's hands, okay? So we're looking at the results here and we're saying, basically now, instead of being given one of the final velocities, we're asking what would both of the final velocities be, okay? So let's run the numbers, see what would happen. We've got our conservation of momentum and we've got our conservation of kinetic energy. So it's very easy just to plug numbers into this. You know, M1 goes in as 0.145, M2 goes in as 1, B1 and D2 go in. What happens? Okay, so there's the numbers in there. And obviously, algebra here, class-like terms, we get an equation with two unknowns, no surprise, just like last time. And then the numbers are going in here. Again, same deal, no surprise. Two equations, two unknowns. So we have to combine those, of course, by substitution and see what the final velocities of the ball and the bat will be. So do you want me to leave that slide a little bit, anybody?
I think it's okay.
It's okay?
But yeah, but I wasn't completely sure on the importance of the follow through.
Oh, the follow through. Yeah, that's the idea. Like if you picture the final velocity here, like if the final velocity of the bat was a lot, well, final velocity of the bat was a lot slower, then basically instead of the energy going to the ball, it goes to the bat. Like it's, yeah, the follow through does two things, right? It pushes on the ball longer too, if you're thinking about the impulse and change momentum, right? You're pushing on the ball longer if you're following through rather than like letting the bat go back and stop contacting the ball quicker, right? So I think that's probably the easiest way to think of the follow through mattering. It doesn't matter in the context of these numbers though, of course, right? We're just saying, well, we've got numbers we're given here and we're going to figure out what the final velocities are of both of these objects. So if people are just sort of following along, knowing the lesson's going to be posted and you have the video, then you're probably fine. If you're trying to write stuff down, I'd imagine you need time. So that's really what I was asking, if we need time or not. Do you have any further questions though, Sarah?
I think that unfortunately I understand. Like it's just a bit confusing. Like with like the broken bat, the time is increased, and so it doesn't go as far. But in this case, the time is also increased, and that's keep going farther. Like there's a part I missed, but that's just
right. Where that does sound a little contradictory, right? For sure, I'm with you on that. So I might not have phrased that as good as I should have. The bat breaking clearly allows this force to be a lot less, though, doesn't it? Right? Because it's the ball's like breaking through the bat instead of the bat like maintaining its structure and applying a ton of force to the ball. So you are very smart and very astute, and you picked up on a little bit of a contradiction in what I was saying. overall, of course, what I'm saying is true, but the way I've explained it is a little contradictory, if that makes sense. So when you're following through, you're applying the big force. It seemed contradictory, I should say, right? When you're following through, you're applying the full big force for longer. So that's going to get you more energy. So that's a separate situation. And that should make sense in its own right. Then in this other case where even though you're trying to follow through, the bat breaks, well, what the bat breaking might do is might allow, yeah, I don't know if I want to talk about that version of it, but basically the force doesn't remain the same. I think it's the better way to say this, right? So maybe it's a little bit dangerous to use this analysis here for that. Instead, I want to just focus on now to fix it here, that force drops way down when the bat breaks, right? And so, yeah, I might rejig that next time I say it. That happens when I have smart, observant, critical thinkers in my class, and I love it. So I'll fix that. I'll modify that a little bit next time I deliver this topic. Good job, Sarah. Does that help enough?
Thank you. That makes more sense now.
That's cool. Good. I love it. I love it. All right. So we've got these two equations, two unknowns. We're of course going to combine them, solve for one of the variables, whichever one's easiest. Clearly the V2 is the easiest one in this case because it's all by itself, right? Not that V1 would be that hard to solve for, but I don't have to divide if I solve for V2. So V2 is this. I'm just trying to grab my purple pen here. V2 is that thing there, so that's going to go in for V2. And we're going to have to pay attention to the whole square of the binomial thing again. So I've got it underlined, and I just, you can see it's all worked out. Right? I've got this thing squared, I've got that times 2, I've got this thing squared, it's all good. Common mistakes, of course, missing the 2, so don't miss the 2. Another common mistake is this stays as a negative. Don't do that, because that's wrong, right? Because you're getting a negative times a negative, so you get a positive answer here, right? So this positive right here is because we're squaring that negative, right? Negative times a negative leads to a positive. So I'm just highlighting some common errors. But long story short, we end up with a quadratic. It's a full quadratic. So we do the quadratic formula, and we get these answers. I'm not showing the details of the quadratic formula. You can work that on your own or use an applet if you're good at it and it just takes time, then use the app. So could the final velocity of the bat be the same as it? Is that right? Same as what it was? I don't know what that's saying. V1 prime. I forget which one's which. Basically, we're saying that one can't be the same as it was. I have to look at the numbers we started with. So we're getting, instead, a final velocity of the ball. Yeah, this is for the ball. Sorry, this is for the ball. The ball is coming in at minus 41. It can't stay at minus 41 because you're hitting it. So instead, it must end up being 69, which if you multiply by 3.6, is a 250 kilometer per hour exit velocity. That's what the ball exit velocity would be if it was an elastic collision. Instead of being, whatever we had last time here, we had an exit velocity of, what did they say? It's way more obviously now, right? The exit velocity we figured out was, they said it was 49. So 49 times 3.6, 176. It's still really fast, but it's close. I roughly say it's close to doubling the exit velocity. Like it's going to be pretty obvious, right? So I jokingly say, yeah, sure, nobody will notice. Go for it, Houston. The bat speed. What happens to the bat speed? Since the ball is going off with so much more velocity, right? Let's see what happens to the bat. The bat ends up slowing down even more. Okay, so it would feel different too for the players. Right, the bat would slow down more in their hands. It'd probably hurt more because the bat would change so much more drastically in your hand, and the vibrations would probably be more as a result. But yeah, so a springier baseball would go way farther, and it would be very noticeable. So I think that's neat that we're able to analyze what would happen in the implications of this elastic collision stuff in a sport that a ton of you are certainly familiar with. We've all played baseball in phys ed at the very least, right? Whether you're a big baseball fan or not. So it's neat. Yeah, so and MLB and Major League Baseball puts a lot of thought into their baseballs. They modify them once in a while to change the game for the better, and hopefully they try to anyways, right? For a while we had there was a dead ball era, so they had balls that were not very elastic, and it was called the dead ball era. So there was very few home runs, and people got bored. So then now they for a while they had balls that were heavier and nice and springy, and so we had tons of home runs. And then this year they actually have balls that are a little lighter, I think is what I'm remembering. And so because they're a little bit lighter, they have more air resistance, and so people are having trouble hitting home runs this year because of the new balls, the newly designed balls. Last year they had new balls actually that were causing people to get blisters. So anyways, I will post this stuff. This is a little heavier, obviously. Reality is we've got a grade 12 physics course going on where we're doing 2 lessons per day. So you need to put some time into this if you're planning on getting a grade 12 physics course in a quarter of a year, or half a semester, I should say, of course, right? Double time to get it done in half the time. So luckily you only have 2 courses though, right? Anyways, sorry, I can always keep trying to justify that, honestly, because I feel bad that quadmester is happening, but I'm here to help. All the solutions are made to help make it efficient as possible. I do have some other, watch for the details here of what I'm suggesting, right? But any questions? I will be saving, PDFing, and posting all that stuff for you momentarily. And I won't be doing a virtual help session at 1 today. But if you need help, email me and I'll help you through, but based on need, rather than definitely logging in. Okay. All right. So I will turn my mic off. Stay nearby here for quick help if you need. Until noon, but I'll get uploading, and I don't want you to hear all my clicking here, so I will sign out audio-wise.
I think you still have to stop the recording.